Okay. We're going to take molarity and use solution stoichiometry. Right, so this is like the stoichiometry we did in chapter 7, where we went from grams to moles, moles of one thing to moles of another, and then back to grams. Now we're going to look at it using volume. Since we know that molarity we can use as moles per liter, and it's a conversion between moles and liters of something. So we're going to focus on taking the volume of something, converting it to moles of one thing, and then to moles of another, and to volume of another, or that same thing. And we're going to use that using our balanced equation. For example, here we have this balanced equation. We have 2 moles of potassium chloride reacting with 1 mole of lead nitrate to create 1 mole of lead chloride and 2 moles of potassium nitrate. In this problem, I want to know the volume of my potassium nitrate when it completely reacts with the lead nitrate. So I want to know the volume of potassium nitrate, but I'm starting with the volume is potassium chloride, but I'm starting with the volume of lead nitrate. So I want to go here from lead nitrate, and I'm given enough information to do this, to potassium chloride. So I know if I'm going to switch my compounds, we have to be in moles, right? And so the first thing I'm going to do is get to moles of lead nitrate. And I'm going to do that using the molarity of lead nitrate and how much lead nitrate I have. So I can do that and go to moles of lead nitrate, and then I can go to moles of potassium chloride. And then from there, I can go to liters of potassium chloride using the molarity of potassium chloride. Okay, so putting our strategy out there, we're going to take the conceptual plan of moles of volume A to moles of A, then to moles of B using the coefficients of the balanced equation, and then we're going to go to volume of B. So here's our plan. We're going to take the liters of lead nitrate, go to moles of lead nitrate, and we're going to do that simply by using the molarity. Then we'll go to moles of lead nitrate to moles of potassium chloride using the mole to mole ratio, which is going to be 2 to 1. Okay, and then from there we can go to liters of potassium chloride using the molarity. All right, so here's all my relationships. I have the molarity of potassium nitrate. I know my mole to mole ratio of the two components I'm going to be comparing, and then the molarity of my potassium chloride. All right, so using that conceptual plan, here we go. We're going to go from liters of lead nitrate to moles of lead nitrate using the molarity, so my liters cancel. Once I'm in moles of lead nitrate, I can go to moles of potassium chloride using that mole to mole ratio. And then from there, I can use the molarity of the potassium chloride to get to the liters of potassium chloride. And I should end up with 0.350 liters. Okay. All right, so let's look at this one. What volume of 0.150 molar of nitric acid will completely react with 35.7 milliliters of 0.108 molar sodium carbonate, according to the balanced equation? So again, I want you to recognize that we're going from one compound to another. So we know we got to get to moles. We have enough information to start with my volume of sodium carbonate. I can go to moles of sodium carbonate. Oops, sorry about that. See if my this will work a little better here. Okay, go to moles of my sodium carbonate, and then I can go to moles of the nitric acid, and then I can go to my volume of the nitric acid. So step one, here we're going to use molarity. Here we're going to use the coefficients. And here we're going to use molarity again. So I'm going to, molarity is moles per liter. So this needs to be in liters. So that's 0.0357 liters. So that's going to be the first thing I do is take liters of my sodium carbonate. I'm going to multiply it by the molarity to give me moles of sodium chloride, or sodium carbonate. So that'll be moles of sodium carbonate over 1 liter. All right, and then I'm going to multiply that, so those liters cancel. So now I'm in moles of sodium carbonate. I can go to moles of the nitric acid using the mole-to-mole ratio, and it's going to be 1. So the sodium carbonate will go on the bottom. So I have 2 moles of nitric acid over 1 mole of sodium carbonate. Right, so then the moles of sodium carbonate cancel. And now I can use the molarity of the nitric acid to go to liters, because I know that there is 0.150 moles of nitric acid for 1 liter. The molarity tells me that. So that gives me, if I do the math, that gives me 0.037 or 57 times 0.108 times 2 divided by 0.150. So that gives me 0.0514 liters of nitric acid, or 51.4 milliliters. Okay. All right, the next thing we're going to look at is looking at types of aqueous solutions and their solubility. Not everything dissolves in everything. So there's a saying, and it's called like dissolves like. Polar things dissolve polar things, non-polar things dissolve non-polar things, and the two don't generally mix if between a polar and a non-polar. Now, if I have something soluble, it is going to make a homogeneous mixture. And let's look here. When my solute, like salt, like sodium chloride, table salt, when that is put into water, we know it dissolves. Why does it dissolve? We've talked about this before, but it dissolves because of interactions with each other. Water is a polar compound. Oxygen is more electronegative than hydrogen, so it has a partial negative charge. Hydrogen has a partial positive charge because of the electronegativity difference. Sodium chloride is an ionic compound that breaks up into ions when it goes into water. What happens is sodium chloride will go in as a solid, and then you'll see it disappear, right? Well, what happens when it disappears is that sodium chloride breaks up into its 2 ions. And the reason it does that is because of the partial negative charge on our oxygen attracts the sodium towards it and pulls it apart from the chloride. And the negative charge of the chloride is attracted to the partial positive charge of the hydrogen. So it separates the sodium and the chloride, and that's actually what's happening when you don't see it anymore. So it's causing it to dissolve. We call that solvent-solute interactions. So here's just another picture that is showing you. We're talking about an aqueous solution. We're talking about solvent being our water, and water dissolving solute like sodium chloride. So here's our oxygen, here's our hydrogens. And because of because of that electronegativity difference between the oxygen and the oxygen carries that partial negative charge. So it attracts the positively charged metals from our ionic compounds. Okay. So, and we see that right here. This is just another picture showing you that the sodium and the chloride will come apart from each other. In water, the chloride will be attracted to these positively charged hydrogens, and then, or partially positively charged, and then the sodium to the oxygen. Okay. Now, when I have things like sodium chloride dissolve, and they form ions. So the sodium chloride, we know when we put it into water, we just learned that it exists as sodium ions and chloride ions. When I have something that can exist as ions in our aqueous solution, they can serve as electrolytes. Electrolytes conduct electricity. So if I have sodium chloride going into my water, and I'm going to have these ions floating around. The ions can conduct electricity, and so if I were to put electrodes in there attached to a light bulb and a battery, it would light up the light bulb. There are certain things that when they dissolve in water, like sugar, that don't break up into ions. We call those non-electrolytes. And what happens is if I have a sugar molecule that looks like this, it's going to look like this in here. Although it's dissolved, it hasn't broken up into ions, and therefore it cannot conduct electricity. And here's just a picture of that. Here's a sugar molecule. It is attracted to the waters, and it does dissolve in solution because of that attraction, but it doesn't break up the sugar molecule into ions like we see with chloride. So ions make it be able to conduct electricity, which makes it an electrolyte. If I don't have the presence of ions, it's going to be a non-electrolyte. Sorry about that. Okay, so there are two types of electrolytes. There's strong electrolytes and there's weak electrolytes. Strong electrolytes 100% ionize. So that means that all of my solid, when it's put into the water, all of it will break up into ions. We call that complete dissociation. My weak electrolytes, they only partially ionize. So my weak electrolytes, you'll see this double arrow. That means that it exists in its molecular formula, and then it will also exist into ions. If I were to put one of those light bulbs into each one of these, this one would light up the light bulb strongly because it has more ions. This one would only partially ionize or light up the light bulb because of its lack of so many ions. Molecular compounds, like our sugar, they're non-electrolytes, so they won't light up the light bulb at all, and they will not break up into ions at all. So what are strong and weak electrolytes? Most of our ionic compounds are strong electrolytes. Most of them will completely dissociate into ions when they're put into water, like sodium chloride. Acids and bases are also electrolytes. Strong acids and strong bases are strong electrolytes. Weak acids and weak bases are weak electrolytes. And then, of course, our molecular compounds like sugar, they are non-electrolytes. Here's just a picture showing that. So here we have an ionic compound. It's a strong electrolyte. Here we have a weak acid. I wouldn't expect you to know that at this point, but if I told you it was weak acid, I would expect you to be able to tell me it's probably a weak electrolyte. And here I have a molecular compound, and so you would know that that's a non-electrolyte. Okay, so let's talk about our ionic compounds. Not all of our ionic compounds are soluble in water. If they dissolve in water, they're considered to be soluble. If they don't, they're considered to be insoluble. There's some rules to which ones are soluble and which ones aren't. Here, for example, are two that one is and one is not. Solid silver nitrate. Silver nitrate is soluble in water. It is a strong electrolyte. But silver chloride is not soluble in water. So if you put some silver chloride into your water, you're still going to see it. It's not going to dissolve. All right, so which ones will dissolve? Here we go. So you'll get this on your exam, but you should print this out as you're doing your work. These are probably the most important ones to just really memorize. If in my compounds I have any one of those ions present, doesn't matter what it's attached to, it is going to be soluble. Okay. Then these are also soluble with some exceptions. So for example, if I look here, if chloride is paired with silver, it is insoluble. So if any of those are paired with silver, mercury, or lead, they are insoluble. Sulfates are generally soluble unless they are paired with strontium, barium, lead, silver, or calcium. Okay. Hydroxides and sulfides, they're often generally insoluble, so they're not soluble, unless they're paired with something up here. Same with sulfides. And here are the exceptions for when they are soluble. All right, and then our carbonates and phosphates are generally insoluble unless they are paired with something back up to this point. All right, let's use it. So take a second and look. All right, lead chloride. So let's go back. I have a chloride, which chlorides are generally soluble, but one of the exceptions is lead. So lead chloride is not soluble, or it's insoluble. Okay. Copper chloride. Chlorides, again, are generally soluble. Copper is not one of our exceptions, so copper chloride is soluble. Calcium nitrate. Nitrates are always soluble. It's in that first group. Then we have barium sulfate. All right, there's something about sulfates, so let's go back. Here we go with our sulfate. Sulfates are generally soluble. Is barium an exception? It is. So then this is insoluble. All right, so you just have to be able to use the rules. If you can use the rules, you're in good shape. All right, sorry about that. We can do these ones too if you want. Nickel sulfide. Sulfides are insoluble and nickel is not an exception, so it's insoluble. Magnesium phosphate. Do we have any rules for that? Phosphates are generally insoluble and magnesium is not an exception. So this is insoluble. Lithium carbonate, this is soluble. And ammonium chloride, ammonium is always soluble. All right,